and we can't do that in one webinar. So we divided it into 4 webinar series. So in today's talk, I'm going to cover the basics of nanoindentation, why we are doing nanoindentation, how we are doing it, what is it relations to macroscale mechanical testing, and all of those things. So that is what I'm going to cover. It's going to be very basic. And it's all about mechanical testing. And there are many forms of mechanical testing that you can think of for bulk measurements, for example, tensile, compression, fracture, bend test, friction, fatigue, creep, ductility. There are so many of those. And it is for to understand the mechanical response of material under different functions. And that is what is very important if I want to develop material as well as for a particular application. So among that mechanical testing, harness is one particular testing of interest, and that is what I'm going to cover today. And harness testing is a very old technique. It's more than 100 years old, and I think most of you probably already familiar with some of this harness testing. For example, Brinell or Vickers or Rockwell harness. There are 3 famous harness testing. Even today is been in practice in most of the industries, even in academic institutions. So what is harness testing? Harness testing is basically a measure of resistance to plastic deformation, and that is being done by understanding the penetration resistance of a hard indenter when you try to penetrate into a material. For example, if you take a ball indenter and you apply a stress on a material, it's going to create an impression. And if you know what the load you apply and if you know the size of this impression, you can figure out what is that the hardness of the material, namely by taking the load divided by the projected area of contact will give you kind of a measure of the plastic resistance to the material or the hardness of the material. Okay, so this is very old technique. It's more than 100 years old, and Brinell was the one who started this a long time ago. And in Brinell test, what is done is basically you take a spherical ball, you hardened carbide or something, and then you apply the load onto the material and measure the impression, just I mentioned just a few minutes ago. So why we want to do harness testing? Whereas we are all familiar with the macroscale tensile or compression testing, where you take a sample, you apply a tensile stress and measure the elongation as a function of stress that you apply. Or you take a pillar or a sample, cylindrical sample, compress it and measure the yield stress as a function of the strain that you apply. That is all well-known techniques. So why do you want to do this harness measurement technique? One of the advantages of doing harness measurement technique is basically it is very local, even at macro scale. For example, in this ball indentation of Brinell ball indenters, it's basically within millimeters, you can go do an indent. So it's very local and it is very fast, as well as it's much easier to do compared to developing or making a tensile sample and doing the test and doing all those things. So it's very simple technique. And that is one of the reasons why harness testing is very useful in industry as well as in academic area. And there is a way to connect the harness that you measure to the yield stress that you measure from other bulk testing technique like tensile testing technique. For example, if you measure the harness and if you multiply it by 3, it is approximate to the yield stress of the material. That the 3 times that comes mainly because of the constraint. For example, when you do the material testing and tensile testing, it is basically a uniaxial testing. You apply stress along an axis and you measure the response. Whereas when you do the indentation, you're indenting on a semi-infinite plane, and there is a constraint as you press and try to deform the material. There is a constraint by the surrounding material. Because of the constraint, it finds much more resistance. That is what it gives you 3 times the yield stress. So, and the state of stress under indentation is much more complex than the uniaxial tensile test. And because of the complexity, basically, when you do the indentation experiments, you apply a complex stress state, for example, 3 times 2/3 hydrostatic or 1/3 shear. And so it's a complex test state, but still it is more local. It gives you information that you want to know about the plasticity of the material much faster. So that is the reason why you do this harness testing. And in Brinell harness test, it's all, like I said, it's more than 100 years old. You make an impression by applying a load. And if you know the diameter of the ball that you use, and if you know what the impression that it makes, by measuring d as well as small d, and by knowing the load and taking the load and divided by the total area of contact, you measure the hardness as a number, and that will give you the kind of resistance to the plastic deformation. Okay, so if you take the projected area of contact, for example, if you take the load divided by the actual projected area of contact, you will get a number which is basically developed by Mayer, again, about 100 years, more than 100 years ago. And that will give you kind of a unit, which is basically in Pascal, newtons per meter squared. And that is basically the resistance to the plastic deformation. Okay, so the important thing is that you need to have some kind of a ball geometry, and you apply a stress by applying a load and measure the impression that you create carefully. So when you measure the impression, for example, like you measure the diameter at two perpendicular direction, and from that you calculate what is the diameter of that impression, and you do all this measurement from that measurement. Okay, so what is the problem with the Brinell's tester? Basically, when you do ball type indentation, when you do as a depth as a function of a load, it is not geometrically similar. What I mean by geometrically similarity, for example, when you do an indentation, as the depth increases, the area also increases. But if you take the depth to area, that has to be constant, whereas in Brinell test, it is not a constant. Okay, so that is one of the disadvantages of a ball type test. And the second thing is, like, you have to measure the size of this contact. So I mentioned that you measure it to a perpendicular direction. So it's more of an arbitrary, subjective to a person that who is measuring, and that may give errors. And third thing is, these balls are made of carbide materials. They are hard, but they're not that hard. So when you apply very large forces, they may also deform. So all these three are the three distinct issues that you will find with Brinell harness testing. So to improve that, Vickers harness testing came, whereas Vickers harness test use a probe, which is basically a pyramidal probe, and because of that, it's a square pyramid. And when you make an impression, you make a square impression. And if you measure the diagonals, it's much easier to measure because you have two endpoints that I've clearly shown over here. So you can measure this diagonal lengths at two perpendicular directions. So there is no ambiguity in measuring these diagonals. And then third point is basically these Vickers harness tester are made of hard materials like diamond. So the elastic deformation of those diamond probes are limited compared to carbide balls. So it's an improvement from Brinell. Vickers harness test is an improvement from Brinell. It kind of reduces the ambiguity in measurement, and that's why Vickers become very famous once in 1929. And in deciding the fact for what should be the shape of this Vickers harness probe, there was a lot of work done at that period of time. Yes.
Yeah, I think your voice is coming, back and forth when you're moving, right? Your voice is so.
I'm actually okay. I'm going to keep my mic closer. I'm sitting at same constant distance. I don't know why it is going up and down.
Okay, sure.
Good, no problem. So, when they wanted to compare the Brinell harness test, the harness that is measured by Brinell harness test, they did a statistical analysis where they found that when the depths are 3/8 of the diameter of the ball, it gave much better statistics. So if you do a simple, like for example, if you have spherical indenter, let's say if you have the depth of penetration 3/8 of the diameter of the probe, and you get 2 points, and if you put two tangent, the included angle between these two tangents is about 136. That is the story why we have this 136 in a Vickers harness tester. The included angle is about 136. The reason why I'm telling you is that this has been carried over to Nanoindentation, and there is a reason why it's all coming through. It started from Brinell, and then to Vickers, and then to Berkovich Nanoindentation tips. So there's a story to it. That's why I'm kind of covering that. So, so when you have this 136 angle degree, it kind of approximates same depth to area as you do it with the Brinell ball indenter. So that is the reason 136. So it's a four-sided pyramid. It is made of diamond. So in Vickers harness test, what you do is similar to a Brinell harness tester. You apply a load, measure the impression, basically two diagonals of this impression that you make through an optical microscope. And using this simple equation, you can calculate what is the harness number. It's basically 1.85 times force divided by d squared. D is basically the average of two measurements of the diagonals, and that gives you the number. And Vickers harness test has been in use for more than 100 years now, and it's been regularly used in industry. And with the Vickers, you can also do at smaller sizes, basically, and you need an optical microscope to see the size of these indents. And so the limits of this Vickers harness tester is the resolution of the optical microscope. Okay. So in another form of harness testing is the Rockwell. I think most of you probably already familiar with that. It is almost similar to depth sensing nanoindentation that I'm going to talk about in detail, where what you do is basically you take a conical indenter with a spherical tip and you apply a load. And for doing that, what you do is basically you apply a preload so that you kind of squash all the asperities on the sample surface. And then you apply the load that you need to apply. That is what it has been shown here, force as a function of time. You apply a preload first and then apply the actual load that you want to do and then unload. And then you measure the differential depth, basically from the preload to the maximum load that you did. You measure the penetration depth, and that penetration depth gives you the number basically as a resistance to plastic deformation. Basically, you take a scale and you take the differential depth and divide it by this unit S. S is basically a scaling constant, and is also scaling constant depending upon different scales that you use in our Rockwell harness tester. And from that, you calculate this number, and that is the Rockwell harness tester. So Rockwell harness tester is kind of a very fast because you don't have to measure the size of this indent. You just apply the load and measure the penetration depth, and that straight away gives you kind of a number. So Rockwell kind of harness tests become very famous for industry because they don't want to waste time in doing and measuring the size of these indents. So if you go any foundry or an automobile industry, you can see there are a lot of a number of Rockwell harness tests. So even today it is being used. And what it measures is basically the differential depth of penetration for a given load. So in most of this thing that I've been talking in harness testing, what you do is just you apply a load with a probe of known geometry and measure the depth of penetration or the size of the contact, that size of the impression that it makes. So it's basically that is simple as that I can tell you. You need to apply a load with a probe onto a sample, and you should know the load that you apply and measure size of the contact either by an optical microscope or the penetration depth of the indenter into the material. And if you know the load and you know the characteristic size that you measured, either the size of the contact or the depth of penetration, using this combination, you can come up with some kind of a number. That is what is called harness number. It could be a Brinell or a Vickers or a Rockwell. This is what happens with the macroscale mechanical testing. So most of this thing requires some kind of a measurement in terms of a strain, for which I mean is basically either depth or the size of the contact. And the best thing that you can do if you measure with an optical microscope is limited by the optical resolution, and that is the best you can do. So there is a length scale limitation that has been imposed because of the resolution of the optical microscope. So how do we wanted to go and measure properties at nanometer length scale? And why do we wanted to measure the properties at nanometer length scale? That is what I'm going to cover in the rest of my talk. And this is just the basics for introduction. So for example, the thing I mentioned about tensile test, I'm going to go show you on a video of the tensile test, just to recap. And in tensile test, what you do is basically you grip the sample and you apply a stress along this axis, and you measure the elongation as a function of the load that you apply. Then if you start to see, you have the stress strain curve, and you also saw that the material started necking at some point and then it fails, right? So you have a distinct signature of this load displacement or the stress strain curve response from the simple tensile test. And you can measure what is the yield stress of this material, or if you take the slope of this initial loading, and that will give you the Young's modulus of the material. So in a simple tensile test, you can measure the Young's modulus as well as the yield stress of the material. So now let's say that you take this material and make it smaller and smaller, okay? This is a bulk sample, and you can make it in a millimeter length scale or in less than a millimeter length scale or to a micron scale. And if you ask this question, now if I can go and measure this property as I reduce the size scale of this material, but keep the same geometry, I'm going to measure the same yield stress of the material. Young's modulus, you will measure the same material property. Young's modulus is not going to change with the size scale because it's an intrinsic property. But the yield stress, as we all learned in old days in metallurgy, we all thought that the yield stress is scale independent, but that is not true. Over 3 or 4 decades ago, that it's been discovered that if you reduce the size scale and try to measure the property, you can see that the measured property is not the same as the macro scale. So that yield stress is not scale independent, it is scale dependent. That is one thing that we need to remember. So which means that if you go from micro to nanometer length scale, the strength that you measure may not be the same as you measure from the bulk mechanical property measurement. This is one thing that is very important. And that has been even shown, for example, in 2005, the work done at the Army Research Lab here in US clearly shown that if you reduce the size of these pillars are basically for compression experiments. As you reduce the size, you can see that there is an increase in strength, and that is being done by different groups, and they kind of validated that point. As you reduce the size scale of this material, the strength increases, okay? So around the same time, we developed an instrument that works inside a transmission electron microscope. So at that point of the time, there was a lot of theories came out to say why you have an increase in strength as you decrease the size of this material length scale, and the multiple theories. And so when we started doing these experiments inside a transmission electron microscope, we kind of found out what is the main reason. So you can see that this is a pillar, this is a probe that is compressing this pillar. And you saw it in the beginning, you saw that the pillar was full of dislocation. That's why it was very dark. I can show you the video again. And see that in the start, you can see the pillar is full of dislocation because fibbing and the process of making this pillar introduce a lot of defects close to the surface, and that's why you see that it's a dark color. And as you compress, you can see all these defects are moving out, and it becomes transparent, almost like all the dislocations been driven out. And that is the reason why at smaller scale, for example, like there is a characteristic length scale associated with the dislocation multiplication. For the dislocations to multiply and give strength, they have to move a characteristic length. But when this pillar has a small dimension, like for example, this is the length scale that I'm showing here, about 50 nanometer, by that before it multiplies, it comes out of the surface and it disappears. So that is the reason why the properties are going up and the strength is going up. So we were able to figure that out. So what I'm trying to say is basically at smaller length scales, the mechanical property that you measure is not the same as you measure from the bulk mechanical properties. That is from the fundamental point of view. There are other reasons why you wanted to study the properties of materials at smaller length scale, like nanometer length scale. One of the reasons is basically when let's say you make an alloy which has multi-phase or a precipitates or some inclusions, okay, and you measure the property, bulk property, you see that as you change the microstructure, the bulk property is improving, but you don't know why. We know that because of this microstructure, you have a better property. But if you wanted to understand why that microstructure for example, the precipitate or the second phase is improving the mechanical property, you have to go down to that microstructure length scale, and sometimes even to nanometer length scale. And to do that, you need to go and study the properties at that length scale, and doing for doing such kind of experiments, you can't do with the general tensile or compression test. Maybe you can do a pillar compression test, but the test that which is very easy to do is basically indentation test. Okay, that is what I'm going to talk about, nanoindentation test, in the next few slides. Okay, so what is nanoindentation? I'm going to give you a simple video description of it. Basically, you see in this slide, there's a top triangular part that you see here is basically a diamond indented tip, and the bottom one is the sample surface. This experiment was done inside a scanning electron microscope, and you can see as you bring the probe and make contact onto the sample, as you apply the load, it makes an indent and it makes an impression, right? And while doing that, you also measure the load that you apply as well as the displacement of the penetration depth of this indented tip. Okay, so if you plot this load versus depth, you typically get this load displacement curve within some hysteresis. For example, if the material is very hard and elastic, if you do this load displacement curve, it will completely retrace its path. For example, load and unload, you won't see this hysteresis, it will completely retrace itself. So we call that as an elastic response. Whenever you see this kind of hysteresis with the load displacement curve, that is mainly because of the elastoplastic deformation. It's not only plastic deformation, there is also some elastic deformation goes along with this in the process. And that is the reason you see this hysteresis. Okay, so for example, if the material is highly plastic, you will see this hysteresis is very high. For example, if you load and unload, it will unload to a vertical drop. And if the material is highly elastic, I mentioned that it will have only elastic deformation. So in between, you will see this variation of the hysteresis. Okay, and this is done with the diamond pyramid, three-sided pyramidal indenter. We call Berkovich because it was developed by Berkovich, scientist called Berkovich. And you can have the probe with very small dimensions. For example, typically you can make probes with 40 to 120 nanometers tip diameter. So you can go down to that kind of a scale. Even sometimes sharper probes, you can go up to like 10 nanometers. Okay, so you can go down to that kind of a length scale. And if you have microstructure and a nanostructure, you can go and probe those structure and measure the properties. What you have to do, you have to kind of get this load displacement curve. And from that load displacement curve, you have to kind of infer the mechanical properties. How do you do that? That's why you need to have some kind of an understanding how material deform. For example, you take a probe with, I mentioned three-sided pyramidal probe or a conical probe, whatever the shape is, it doesn't matter. So when you press it onto a sample, what it does is basically you kind of displacing a volume of material depending upon the volume of the cone or the pyramidal indenter that you use. So the displaced volume of this material has to be accommodated somewhere. Metals are non-compressive, basically. So where that material flow. So the material sometimes may flow to the surface for forming a pileup. And sometimes, like when the material is annealed, for example, with a very low dislocation density, that volume displacement will be accommodated within the material, in which case you will get a sinking. So the geometry around that indenter kind of reflects the state of the material, whether it is having high defect density or not. So for example, if you take a copper sample, and if the copper is well annealed so that it has very low dislocation density, if you do an indent experiment on that, what you will see is a sinking phenomena. For example, the indent have kind of sinking. geometry. While if you take the same copper, work hard, and basically you create large amount of dislocation density, and then you do an indent, the same copper will behave differently. It will have a deformation totally different, in which case there's no room for the material to get accommodated. It will pile up to the surface. So even with same copper, depending upon the state, basically it is, whether it is well annealed or work hardened, you will have a two different kind of a response. Okay, so same thing. So that is geometrical observations. And you can also see the same observation on the load displacement curve. Basically, if you have a material and if it is highly work hardened, you will get the load displacement response different from the one with the annealed state. Okay, so that is what is very, very important. So if you have this load displacement curve, and if you know the geometry that you use for doing this indentation experiment, and then from this load displacement curve and from the known geometry, you can calculate the hardness and modulus of the material. How you will do that? That is why you need to have a model, and this has been well established. For example, what is important here is you take a probe, you apply a stress onto the sample so that you're applying a load, and it penetrated to a depth H max here, and this is the material elastic deformation. At some point, the probe is making contact with the sample surface, and this is the height of this contact that you need to know. And if you know what is this contact depth, you can calculate what is the contact size, because it's basically geometry. And if you know, or if you don't know what is the contact size, the contact area, you can do a simple calibration with a material with known property. For example, we use generally a fused quartz sample for which we know the modulus of the material. So we indent on it, and for a given depth, with the geometry of this diamond three-sided pyramid probe, we calculate what is the size of this contact as a function of depth, and we call it area functions. Once the tip has been calibrated, then you can use the same calibrated area function and then use that to measure the property on different material, for example, copper or aluminum or whatever it is. So there is a elaborate, it is easy to say you measure the load and measure the depth from the load displacement curve, you go and measure the hardness of the material. It is easy to say. To make a measurement, a consistent measurement, repeatable measurement, and valid measurement, there is a lot of procedure that you have to go through. You can research through on web. There are a lot of papers, and so there are procedures and there are calibration routines that you have to go through to calibrate the indenter probe and calibrate the indenter system. And once you have done that, from the unloading curve, measuring the stiffness of the unloading curve, and measuring the area function of the probe, you can calculate the modulus as well as hardness of the material. Okay, so but to do that, you need to have some kind of a transducer to apply the force and measure the displacement. So and that's what I'm going to cover in the next slide. So as I mentioned in the beginning, that when you do on the material, depending upon the material that you have, whether it is highly elastic or elastoplastic, you will get different response. It's from elastic response to elastoplastic response. So the load displacement curve that you measure or you get is kind of a fingerprint for the material that you have. Okay. For example, if you do the same experiment on a fused quartz, you have a fingerprint of like this. If you do it on aluminum, it's a highly elastoplastic. You can see the hysteresis is very high. It has a different signature, whereas when you do it on a polymer, it has a different signature. Okay, so this load displacement curve can be used as a fingerprint for the mechanical response of the material, and then you can directly measure the properties like hardness and modulus from this load displacement curve. Okay, so the one advantage of nanoindentation is basically this is a very modern technique, and because of that, you have fully automated system. For example, you have a sample, you can have 5-10 samples on a sample stage, and within the sample, you can go and position this probe at plus or minus 10 nanometer position accuracy, and then it gives kind of a higher resolution spatial measurement. and you can go do a site-specific measurement. And so it is a very simple technique. With respect to technique, you apply a load and measure the depth of penetration, you get the load displacement curve. And with automation, you can go to a resolution with plus or minus 10 nanometer position accuracy, and you can program it so it can do automatically all those places. For example, nowadays we were able to do 1 million indents maybe in 3-4 hours. Okay, for example, 5 indents per second. You can do that. It's all fully automated, and you can do site-specific indentation experiments. Because of the advantage of automation, you can totally do all those things in a relatively short time. Okay. And because of the technology improvement, we are able to make measurements even at higher temperature. So you can take a small volume of material, heat it up to a very high temperature, up to 1000 degrees C, and measure the mechanical property by measuring the load displacement curve. It is a highly repeatable. I'm showing 2 different curves here, basically many different curves here. This is done at 400 degrees C on fused quartz. You can see that how repeatable these experiments are. So their technology has been improved that you can do it higher temperature with a good stability nowadays. Okay, so how it is done? So there are many ways of doing nanoindentation experiments. What you need is a transducer to apply force and measure displacement. Okay, there are ways that you can use physics. Basically, for example, you apply a current through a coil in a magnetic field, you generate force. Okay, that is one way of generating force. And if you have a capacitance-based sensor, you can measure the displacement. So by combining the various way of actuating and measuring the displacement, you can have different type of transducer. The way that I'm going to show is basically using electrostatic force actuations. What is it? So if you take, for example, in physics, if you have 2 parallel plates, right? And you apply a voltage between these parallel plates, you generate an electrostatic force. It's similar to, like, for example, you take a comb, rub it on your head, and bring closer to your piece of paper, the paper will jump to the comb because of this high voltage difference between the paper and the comb that you have. The same thing, if you can apply a high voltage difference between these plates, that will generate a kind of attractive force. And that force is scaled to basically the capacitance of between the 2 plates, C1, and the spacing between these 2 plates. So if you know those things, this is a constant, and depending upon the voltage applied, you can vary the force. So it's a very simple thing, a very simple concept. So if you have a geometry where you have a 3-plate capacitance structure, where the center plate is suspended, and you have 2 outer plates, by applying a voltage between the center plate and the bottom plate, you can generate force. Right? So that is how it has been done. So you can generate, in this particular case, depending upon the size and the shape of the transducer, you can generate anywhere from, say, micronewton to tens of millinewton. And typically in our transducer, we were able to generate about 10 millinewton to 25 millinewton force. Okay. So the force generation is easy, and it is easy to control by applying the voltage. By controlling the voltage, you can control the force. How do you measure the displacement? This is a 3-plate capacitance structure. So the center plate is moving in between 2 outer plates. So the capacitance is going to change depending upon the center plate position based on this particular equation. Okay, that is also same thing. Basically, if you know the capacitance C1 and C2 and the voltage that you apply, you can calibrate and then get the displacement from the capacitance measurement. So in the same structure, you are able to apply force by electrostatic means and then measure the displacement through capacitance mean. Okay, so that is how this transducer works. Now, if you fix this transducer on a piezo scanner, for example, 3-axis piezo scanner, where the scanner can move in X and Y and Z direction, and by combining that kind of a scanner to this transducer, you can also use this transducer to scan on a surface and to generate a surface profile. For example, in this case that I'm showing in this cartoon, where the tip is sliding on the surface in a raster scan pattern. As the tip is sliding, depending upon the morphology of the surface, ups and downs, the center plate is going to go ups and down. And then if you can measure that change in height as a function of as you scan, line by line, you can create a profile. By constructing those profile into an image, you can get a three-dimensional image of your sample surface. So you kind of use this technique for in situ. You can measure this with the surface topography in a three-dimensional way, and you can do that at higher resolution. This is similar to atomic force microscope, but slightly higher scale. But you can do almost like 1 micron by 1 micron scale. You can routinely do, and within like depending upon the tip dimension, for example, maybe 20 to 30 nanometers, the resolution is going to be limited. Within that resolution, you can do a very high resolution imaging with this in-situ SPM imaging. So that kind of gives you kind of a handle on what is there on the surface, a kind of a scanning probe microscope. And once you have that information as an image, you can go and target where you want to do an indent. For example, if you wanted to, this is an image of a wood cell, and you wanted to indent on the cell wall, you can bring the probe and target that particular position and do an indent experiment. Okay, so this is a very useful feature, and we call in-situ SPM imaging. This is a two-phase material. You can see there is one phase here. This is the ceramic phase. You can target that particular phase accurately, and then you can do an indent. After the indent, you can come back and image to this raster scan procedure that I mentioned, generate the image, and that will give you kind of an idea where you indented, what is the size of this indent, and all of those information. So this is very useful. So it's much useful. I mean, for example, if you wanted to make a measurement, you need to know where you are making a measurement. You need to have some kind of an idea, what is the geometry, what kind of surface it is, for example. Okay, that optical microscope is limited because of the resolution, as I mentioned before. With scanning probe microscope, you can go for high resolution imaging as well as positioning, and you can do an indent in a precise position within plus or minus 10 nanometer positioning capability. Okay. So, and it can use the same imaging technique. It can do advanced imaging. For example, you can map the property of the material. We call it modulus mapping. I'll be covering in the next in a webinar about that. You can do tribological characteristic. For example, instead of measuring just the normal force, you can also measure the lateral force in a two-dimensional transducer. You can do a friction imaging. Or if you have a conductive probe, you can bias the tip with respect to the sample, and then you can do conductivity at point to point in pixel by pixel, and then you can do conductivity imaging. So there are many forms of imaging that you can do with this transducer. And in combination with this image, you can also do mechanical testing. Okay, so this is a particular example. This is a diamond-like carbon thin film on a steel substrate, and this image is generated through SPM imaging, and you imaged on the surface, and you can see that from the image, you can get the thickness of this thin film that is on the surface, which is about 129 nanometers. And then you can go position at different positions from the substrate to the thin film, and we can make a measurement. You can do this low displacement curve measurements, and then from that, you can calculate the hardness and modulus. These are all the low displacement curves. Then the blue curve is for the steel. The yellow curve is for the diamond-like carbon coatings. And you can see that how the low displacement curves are different from different region. And from this low displacement curve, as I mentioned before, using those models, you can calculate hardness and modulus. And then you can see the variation as you go from substrate to the film. Okay, you can directly measure those properties pretty easily. Okay, can do that on other materials. For example, this particular application is for semiconductor packaging. This is a solder ball on a copper, and you can see that this is an image generated through SPM imaging. You can see this is the copper structure. This is for semiconductor, where you kind of use this for packaging IC chips on a substrate to get the electrical connection. And the top part is the solder ball, and the bottom one is the copper. You can see that indent's been done across a line, and you can see the indent response. For example, this is at the interface, IP is at the interface. copper over here, and then this is the solder ball. You can see the load displacement curves are different at different region. And then you can go calculate the modulus and hardness. For example, you can see that the silicon has much higher modulus. It's about 140 GPa. And then you can see for copper, it is less. And then you can see for different stack of this material, in one setting, you can go and measure the properties across this whole length, and you can measure at different points for different material, how the property is changing as a function of position, right? You can do that for harness as well. So with the SPM imaging, you are able to go and see where you want to do indent, like how I am showing here, and you can also position it across the surface or across an interface, and you can measure those properties. Okay, this is another example. This is a typical thing that you do with the steel sample. This is an optical image, and this is an SEM image. And what you see is basically martensites and ferrites in a DB780 structured steel. And with this image, the In-Situ SPM image, I'm able to go and see where the martensites are and place my probe and do an indent. You can see these triangular indents on those parts. I can also do it on ferrite. So I can go and target that particular phase or the precipitates and measure the response through load displacement curve and measure the hardness and modulus. This is another example. This is again for steel. You can see there are a lot of precipitates on the steel. And if you wanted to measure the property of those precipitates, you can go directly and place indents and get the load displacement curve. And from that, you can measure the hardness and modulus. So this is kind of gives you the power of this technology, that you can go and target that particular phase or the precipitate or the morphology, whatever that you wanted to target, you can go and do that with plus or minus 10 nanometer positioning accuracy, and you can measure the response of the material. Okay, you can do it in a grid, for example, in a number of indents in X and Y direction. And in this particular case, this is again a steel, it's a laser cladding. Okay, now you can go and map the structure in using a EBSD sensor in a SEM, and you can see this is how it is coming, and you can see different domains and martensites and other things. Okay, and you can go and do an indent experiments. In this particular case, maybe about 1,000 indents, with an array spacing about 3 micron between the each adjacent indents in X and Y. You measure the hardness and modulus. Now you can kind of see this hardness map correlated to the microstructure that you got information through EBSD. So you can do this, and you can do million indents or thousands of indents in a relatively short time, and you can lay over on the microstructure information that you have, and then you can correlate the microstructure to the mechanical response then and there. So that is the powerfulness of this particular technique. So you can do a grid-based indents in a relatively short amount of time. Okay. So until now, I talked about simple hardness and modulus measurement. Now, if you have a way of attaching 2 more transducers along with this normal transducer, you can apply a normal, along with a normal stress, you can also apply a lateral stress. So that is very useful for topological characterization. For example, in this particular case, you can load onto the sample, okay? And then you can use the lateral transducer to move in laterally and measure the friction response. And so from that, you can calculate them topological characteristics. Or if you have thin films, in this particular case, you can indent, apply the normal load, and progressively increase the normal load as you move the lateral transducer. So at some point, the film is going to debond from the substrate, and that you can see through a jump in the load displacement curve, both in the lateral force as well as normal force. At that point, we know what the critical force is, critical load is, and through proper modeling, if you know what the critical load is, you can calculate the adhesion strength between the thin film and the substrate. So not only tribology, you can also figure out, let's say if you have a thin film on a substrate, the adhesion strength of this thin film on the substrate also can be kind of figured out by doing these crash type experiments. Okay. So now we can also extend to wear resistance. For example, because we have this piezo scanner, the same way that you generate an image by scanning, raster scanning on the surface, you apply at increasing load, normal load, you do the same thing. In this thing, you can clearly see, instead of just imaging, you progressively increase the load so that you can remove the material from the surface, and that you can do at very small length scale. This is a 15 micron square that you can see, and you can do it to a particular phase in a material. For example, you wanted to understand the wear property of one particular microstructure with respect to the rest of the material, you can go and wear out that particular microstructure or a phase or a precipitate, and you can do that in situ. Okay, and you can measure the amount of material that is been removed as a wear volume. That will give you kind of an understanding about this, about the tribological property of the materials using the same similar setup. Okay, and along with material removal, you can also kind of figure out what is the friction characteristics through friction map through the lateral force sensor. Okay, so in a way that it's not only measuring hardness and modulus. With this in-situ SPM imaging capability, with a 2D transducer, we can also go and do tribological characteristic of the material. Okay, and again, one more thing that you can do is you can do, for example, for materials which are very difficult to measure the fracture toughness, for ceramic materials. Okay, you can kind of extend this technique to understand the fracture characteristic of the material by simply measuring the crack that creates when you use certain type of indenters. For example, you need to put a large amount of strain into the sample to crack. So we typically use cube corner tips, and with that you can, with a higher load, you can generate cracks, and through SPM imaging you can measure this crack length, and through indentation you can measure both hardness and modulus, and with the known crack length you can also go and measure the fracture toughness of this material. So with in-situ SPM imaging, that is the key, that you can do all of these things very nicely and in the same setup. Okay, so not only measure the hardness and modulus, you can also use this similar this transducer technique with in-situ SPM imaging. You can go and measure the friction characteristics. You can go and measure the wear characteristics. You can go and measure the fracture toughness of the material. Okay, so that is the power of this particular transducer technology and the way we do. Okay, so with this, we can go and use it for a number of materials, from ceramics to very soft materials. And this example that I have given a lot of examples here, and you can see one of those examples is the red blood cell. Okay, even if it as soft as, for if you wanted to measure the mechanical response of this red blood cell, you can use the same transducer and go and measure the mechanical response. So it's not only for kind of metals that we see normally. You can throw anything under this transducer, and as long as you are able to image and you can see what is there on the surface, you can put the probe and measure the mechanical response of the material. Okay, so that is possible. So that kind of expanded the use of this technique into many industries. I've kind of listed about 15 of those, from polymer industries to automobile industries to aerospace, semiconductor industry, steel industry, foundry, pharmaceutical industry, wood products, building materials, petrochemical industry, structural ceramics. So this is kind of becoming kind of a standard in and a simple way of measuring mechanical properties by simply doing those experiments the way that we want to do. And so it's kind of expanding into different industry, this technology. Okay, so with that, I'm going to give you 2 more slides. These are all the platform systems that is available from Bruker. And then this technology can also be extended into a microscope platform. For example, if you have a scanning electron microscope or a transmission electron microscope, all this mechanical measurement that I mentioned here can be done inside those microscopes, and you can do a direct correlation by observing what is happening directly. And finally, we also developed a desktop system from Industron that can sit down to any academic's desk, and then you can use it. There is a curriculum supported with this instrument. that you can use it for education purpose. And this particular technology requires, unlike like a Brinell Vickers harnesses that you normally do in your lab, nanoindentation is not there in the labs now because of the expense and also the support structure that it requires. So we developed kind of a desktop system that goes into a kind of a lab where students can come and learn. So with that, I'm going to go stop. And we have the second part of this seminar, basically a webinar on 26th November. In that, I'm going to cover about the advanced dynamic nanomechanical testing and high temperature applications. So with that, I'm going to go stop here and handing over to Pratyang and answer your questions.
Thanks, Dr. Asif. It was pretty informative talk. And yes, we have few questions raised by from our attendees today. So first question that I have is, how do we define quantitatively a relative elastic or plastic nature of a particular phase in a multi-phase material via nanoindentation and nanoscratch experiments?
Well, in the last part of my talk, I kind of gave you some examples where you use the In-Situ SPM imaging to go and see those particular phases or the microstructure, and then you put the probe onto those microstructure and measure the low displacement response. Okay, so depending upon the geometry, the size of those microstructure, for example, if you have a precipitate in a matrix, the size of the precipitate matters compared to the matrix. So you can measure the response by what it means. So that needs to be kind of you need to figure it out by proper understanding and modeling. But you can measure the response of those precipitates or the second phase and directly from the low displacement curves.
Okay, I hope that answers your query. The second question I have is how to measure the friction using this instrument.
Also, with the lateral force transducer, you can measure the lateral force.
You can take the slide. You can.
Yeah, you need to slide onto the surface, but when you do this, when you slide, you need to measure the lateral force. For that, you need additional transducers that measures the lateral force. Or you can also use the lateral force to actuate in lateral direction, and that way you can measure what is the force required to move in that lateral direction. And then normal load divided with lateral load gives kind of an idea about the friction.
Yeah, I think you have a slide also, right, on Nanoscratch, where.
Yeah, I have a slide, I think, probably.
You are still sharing, so you can.
Okay. Yeah, so yeah, here basically you have a normal force and you have, for example, here you have lateral force as well as normal force. Then ratio of those will give you a direct measure of the friction.
Right. I hope that answers the query. In case you have any follow-up question, please let us know. Another question that we have is, what is the limitation of SPM imaging technique in terms of grain size? For example, could I image nanometallic materials with 20 nanometer grain size?
Okay, so the resolution is limited by the indenter tip size. Okay, so if you have a very sharp tip, let's say you have 5 nanometer tip, you can image the 20 nanometer grain size. If you have a 40 nanometer tip, you won't be able to do that. So it is limited by the size of the tip radius that you have.
I think in the market, like 30 nanometers is the sharpest tip that is available. Yeah, so that's cube corner. So yeah.
Yeah, with the AFM, you can go very short tips to even about 1 nano, 2 nanometers. There are adamant probes that you can see that they are about 2 or 3 nanometers, maybe even 5 nanometers. You can use they are very sharp. But for nanoindentation, because it's a three-sided pyramid, it has to be quantified. You have a limitation on the size of this probe. Typically, what you get the best is about 30 to 40 nanometers.
Right. Okay, I don't see any further question coming. And I think with that, I would like to thank Dr. Asif then for giving this lecture today. And as we mentioned that we have the upcoming webinar on dynamic mechanical analysis. So it's a hybrid technique to analyze viscoelastic and thin films. So please join us for the next session. Please also note that you need to register for each and every session. It has a unique link. So we definitely need to register for attending all these sessions. I also would like to thank all our attendees today for sparing time from their schedule, and we hope that the session was informative and relevant to your research, and will definitely help you in further understanding, or how this can be used in your current research. So the recording of all these sessions will be available it will be uploaded on our Industron's YouTube channel. We'll be sharing the links with all our attendees. And with that, I would like to thank all our participants again for joining us. And we conclude our today's session with that. So stay safe, and and let's meet in the next webinar on 26. Yeah, any query, please reach me at pratyank@industronnano.com. Thank you so much. Have a great day.
Have a good day. Thank you.
Thanks. Bye.
Okay. So